Good morning, here we are again. It's the physics video lecture. psci 168 video lecture 4. So today I have some demo objects on the table. We're going to be talking about forces. But before that, let's briefly review the astronomy and geometry we've talked about, and I'll give you a little assignment to fill things in. So we had ended with some geometry and some astronomy, namely measuring the shape and size of Earth is actually an astronomy problem. So we had shape and size of Earth, and we had similar triangles, right, as an application. But I want to stick with this briefly. I'll remind us of our geometrical construct. Okay, so these two parallel lines represent incoming sun rays. We've got an angle theta right here, and that's the same angle in this circle representing the Earth. There's the radius. We had an arc length S, and from that we had the ratio S to the entire circumference is the same as the ratio theta to 360 degrees. And from there we were able to calculate, based on the known arc length and the known angle, we were able to calculate the entire circumference of the Earth, therefore its radius. So what about other quantities? What we find out is radius of the Earth I'll go ahead and write it this time, capital R sub E, 6.37 times 10 to the 6 meters. And similar arguments and investigations lead us to figure out the radius of the moon, the radius of the sun, and a couple of astronomical distances. What I'm going to do is write those down here and have you guys look them up and just fill in this table. That'll be your table of astronomical data that we'll be able to make use of in the semester. So yeah, we could title this Astronomical Data here. Right, other. Here's our astronomical data table. We've already found this one, and the other ones I list here, you guys are going to look up. So we radius of the Earth. We want the radius of our moon. R sub m equals. We want the radius of our sun. R sub sun equals. So you'll find those, and a couple of distances are interesting as well. Distance Earth to moon. We'll use lowercase r for that, so that will be R EM will be equal to such and such, and then we'll also have the distance of the Earth to the sun. Check the picture here. Good, yeah, that all appears on the screen. So distance of the Earth to the moon, distance from the Earth to the sun. Earth to the sun, and we'll call that lowercase r e sub s. So these you can look up and make sure you have these distances in meters, right? 6.37 times 10 to the 6 meters, and so forth and so on. This one's going to be about a third the size of this one, or a little less even. And this one's going to be a lot bigger, but always in terms of 10 to the power. Same with the distances. An interesting point about the distance from the Earth to the moon is that it's approximately 60 times the radius of the Earth. So you guys fill this in. And I'll just put a little note here. And you guys should check this out. Our Earth Moon is approximately 60 Earth radii. That'll be interesting. You know, you just do the division and see that that's true. Approximation. A couple more things that will be useful. So these are distances, and you know, we did our version, we did our part for this one. The other ones, like I said, if you have enough time, you can figure those out as well. Some other things here, though, that we want is the mass of Earth, mass of our Earth. Let's go ahead and also get the mass of our Moon and the mass of the Sun. So these, m's of Earth, m's of Moon, m's of Sun, you want to have those in kilograms, okay? So in kilograms, all three of these, and then you're able to compare, and of course in scientific notation, you guys look this up, you'll find it, okay? In scientific notation, then you can easily compare these masses as well. So yeah, that's the first that's homework. Just look them up, complete these tables, and they're part of your notes, okay? Homework, find these quantities. Radius of the Moon, radius of the Sun, distance Earth to the Moon, distance Earth to the Sun, all in meters, scientific notation, and then these masses of the Earth, the Moon, and the Sun. Okay, we'll actually make use of this later on. That'll be interesting. But good, that's our section on astronomy, and we've already made use of the geometrical knowledge we had. Our next topic has to do with what I brought here, my demonstration objects. We're going to talk about force. You know, we're working our way up to energy, but there's ways to go. So we're going to talk about force, and next, force. So first I'm just going to demonstrate a little bit. The idea of a force is that it's a push or a pull. So you can feel it in your muscles if you pull, or if you push, if you lift something, you're feeling a force. So I brought some weights, right? This is a weight, it's a chunk of metal, has weight, and that feeling or that weight is an example of a force, and I can feel that force in my muscles, okay? So the muscle sensation. Now I can drop it on the scale here, and it goes approximately to the 10, okay? So the unit of force that we're using, okay, doesn't go as far. This is actually the better scale for that. That's the push. The pull, I've got a 10 there, and if I lift this thing up, it goes to the 10 here. 10 what? 10 newtons. So let's get started with that material. Force, a push or a pull, and the unit of force is 10 newton, is a newton. Okay, here we go. Here we go, force. That's a push or pull, and initially we're just talking about the muscle sensation. So you could say your muscles are a scale. They allow you to sense a certain amount of push or pull. As an example, comes right out of this, what we call weight is a force, and the unit of weight is the pound in day-to-day life, but here in physics, it's the Newton. So the unit of force is the Newton in honor of Isaac Newton, and we readable Newton, and we abbreviate it just with capital N. So yeah, this chunk of metal here weighs 10 newtons, okay? And for the conversion, which we don't do that much of the conversions, but we definitely want to know what it is. The conversion from newtons to pounds, we have 2.2 pounds equals 9.8 newtons. So once you know that, you can make use of it. For example, you could ask, what is your weight in newtons? Okay. Example. Weight in newtons. Question mark. What's your weight in newtons? That's an S. Okay. Say I have my weight equals, say, 190 pounds. I have to do a conversion, pounds to newtons, and then I realize that I can multiply this by 1 if I write 9.8 newtons divided by 2.2 pounds. Okay. So that would be the conversion factor. Okay. So let's put a note here, right? And you can convert the other way around. Basically, you take this equation, and I say 1 is equal to 9.8 newtons divided by 2.2 pounds. Because I divided both sides by 2.2 pounds. I'm left with a 1 on the left side. And this is a unit. I'm allowed to multiply anything by 1, and so that's how I do my unit conversions. And then I'll get some rather large number there. Okay, so that's how you convert your weight to newtons. But we don't need to, once we know this, we're just satisfied with seeing that this chunk of metal is just about 10 newtons. Okay, so that's the first thing about force. It's just a push or a pull. Now, the demonstration I just did, I'm going to repeat. And you just have to imagine these scales are really accurate, which they're not. But I've got roughly 10 here, and I can make it so that I have 5 on both scales, right? Because 5 plus 5 is 10. And if I have 8 on this top scale here, then I should just have 2. Here we go. If I have 8 on the top scale, I should have 2 on the bottom. And if I pick the thing up all together, I've got the 10 and 0. So that's kind of a quick version of what we would call simple addition of forces. Okay? The forces just add like numbers. So we have force, we have definitions, we have the unit of force, which is the Newton, and we even have this conversion factor. So next I'll go ahead and erase this, and we'll talk about simple addition of forces. So this is one here, we'll call this simple addition of forces, and my demo was that I had my chunk here, which was 10 newtons. I had it on a scale. Okay, there's my scale. And I also had it hooked up to this scale here. Okay. So if I had 10, I could have had, say, 6 and 4 and any other examples you want to put in there. The slogan that goes with this is apparently that forces add like numbers. if I were to glue these things together, I could actually pull up with 20 newtons and I'd have to pull down with 10. So they would even add like positive and negative numbers. But definitely forces add like numbers. You know, when we have the full classroom here and people, we actually have 2 bathroom type scales and we can stand on them with 1 foot in the other, and we see that we can split our body weight and do that kind of thing as well. So forces adding like numbers shouldn't surprise anyone. And I'm calling that simple addition of forces. Now it gets interesting when we take these 2 scales here, and they're pretty much identical, so I'm supposed to get 10 newtons on each scale here. 10, and this one here, let me put this off to the side. This one is also going to hopefully read more or less 10. Good. So they're both the same. I'm going to split the forces between these 2 scales, and I again should get my basic 5 plus 5 equals 10. Okay, let's get this going here. There we go. All right. Yeah, roughly 6.5, 4.5, 6.5, 4, 6, 4, 5.5, 4.5. We're basically getting 5 plus 5 equals 10. So that is simple addition of forces as well. And that's not surprising. But I'm going to extend this demonstration to the following situation. We're going to have the scales out here. There's the hook. And we're going to hold the string something like this, where our 10 Newton weight is right there. And now the question is, what is the reading going to be on the scale? Okay, are we looking at 5 plus 5? Question mark. Is 5? Okay, that's the question. So if you had scales at home, you could do this yourself and see what's the reading going to be. We've just seen with the simple addition, 6 plus 4, 5 plus 5, we're always getting 10. Now we're going to put them out this way. And I'm not going to keep you in suspense. You know, we can start with the 5 plus 5, but as we pull them out like this, we're getting up to 20 plus 20. Somewhere around here, I can feel them bottoming out, so this must be around 20 plus 20. 20 in each scale. How is that possible? Okay. How is that possible? Okay. This is the convincer, this demonstration. So we did not have 20 plus 5 plus 5. We had more like 20 plus 20. The reason is the following. This is called vector addition of forces. Something we have to know. It's going to have some great applications. So vector addition of forces. And the slogan here that I have there is going to be that forces, apparently they don't add like numbers, because we clearly had a 5 and a 5 until we turned it to the side here, and now we had a 20 and a 20, and then everything in between. So forces add like arrows. Vector and arrow, similar expression, okay? So I'm going to, on this picture, by the way, in your notes, go ahead and make a nice sized version of this picture, okay? Not just something in the corner, make a big one that's the width of the page or so, and we can really understand what's going on. So forces add like arrows, and I'm going to draw these arrows. So vector and arrow, think of those as being similar. First of all, let's add a couple of arrows. Suppose I were, and you can literally imagine cardboard cutout arrows. Okay. Suppose I were to add a horizontal vector plus a vertical arrow. Did I say vector? Right now I'm talking arrows. So if I were to add those two, and I'm thinking of the physical arrow, what I would be doing is going over one and up one, and my answer, the sum of this equation, would be this diagonal arrow. That's what it means to add arrows. That's what it means to add vectors. So let's do the same thing here, right? That was just a flexible string. So when I stretched that string, tightened it, that shows the direction of the force that the scale was reading. Okay. What we had then was an arrow that goes across plus one that goes up. And because we have the same thing on the left side, this one that goes up is half of the 10 newtons. It's 5 newtons. Okay. So this one here, get rid of this 5. You'll just put a question mark here. Okay. This upward component, as we call it, is equal to 5. And because of that, I can just take this and scale it. So if I take this length here, 1, 2, 3, 4, and a couple left over, those are those 20 or 22 newtons that you saw me demonstrate with those scales. So these two arrows and this one here, well, you can get that with the Pythagorean theorem. I'm going to call this one here 22 newtons. This is the one we actually saw on the scale. This one is 5. This one over here, it's the same thing symmetrically in that direction, and there's the answer. So forces adding like arrows is very, very important because it allows us to understand structures and other things as well. Of course, they do add like numbers. They add like numbers if they're lined up in the same direction. But if they're not lined up in the same direction, they add like arrows. So that's the big lesson for today in terms of forces. And since we've studied triangles, you realize you can fill in the unknowns here using the Pythagorean theorem. In fact, I'll put this as a homework and just leave some room in your notes, okay, because it'll just take one line or two. But right here for the homework, using this example right here. So we've got a triangle, we're going to label it 5 and 22, and this is x here. I'll just call this x. Find x. And since this is a forced triangle, if we say this is 5 newtons and 22 newtons, then this x has to be so and so many newtons. But that would just be an example with the Pythagorean theorem. Okay. You've got x squared plus 5 squared equals 22 squared, etc. So that, that'll allow you to fill in there. And what you can see is this weight here pulling down, it's actually causing these scales to be pulled in. So if you reverse the direction of this arrow, that's how hard we're pulling in. And the flatter you make a triangle like this, the more tension you'll have pulling in. So, very interesting result. Let me consult the clock right here. So yeah, once we know about forces, the simple addition, the vector addition, we can start talking about structures. Now, you may have had a art history class or something where you went through some of the architectural elements, and that's what we're going to do now. Let's see, in terms of homework, just keeping up here, we had those numbers, astronomical numbers. We want to do a little calculation here just to see how, remind ourselves how that goes. Good. So the next thing I'm going to do is show you some structures. that make use of these force concepts. And what I'll have you then do is download pictures and post some nice pictures. Not post them, print them out and put them in your book as well. Okay, so we have forces here. Good. Structures, we can write structures and forces. We'll start that today and finish that on the next one. But the first thing you may have seen is if you just take two, here's the ground, you take two posts, put something across them. So this is called the post and lintel. So that's one that you can look up and get some pictures of. For example, Stonehenge, famous Neolithic structure in Great Britain somewhere, New York, is a bunch of posts and lintels. But how about, and this is the ground right here, so how about the forces? Well, here apparently we're just looking at simple addition, namely we have some rigidity of this beam on top, and then we would have these posts holding it up, and since these two, let's say we're splitting it in half, then the vector would be like that. This would represent the weight of this lintel. Okay, so the weight of this beam and then the force of the post pushing it up. So that's actually an example of simple addition, and the fact is these objects have to be rigid. They themselves have structural stability. Okay. Shade these in a bit maybe, who knows? Good, so this was simple addition. Example of. Okay. Now the next structure we'll talk about is just a gable, say for a roof gable. And here we just draw the walls of the house. Okay, so you have the walls of the house here. Here's the ground again. And you can imagine a structure like this. Okay. And just to make it more interesting, let's imagine someone standing on top here, straddling it. You don't have to have anyone standing up there straddling it for the same discussion, but what's happening here is the following. We just saw the string like this. Now we have the gable, which is just the inverted version of the string. And what's going to happen is that there's going to be a force down and a force out, right? Force down and a force pushing out, which makes this construction do the following. It has an outward pressure, and the effect of this is to push those walls apart unless you somehow tie them together. If you just had two walls and a gable like this, it would push the walls apart. And substantially, okay, it'd be a very strong force pushing it apart, and that's one of the original architectural problems of how to keep a roof like this from pushing the walls apart. So here we're talking about vector addition of forces. My two red arrows add up to the blue arrow, and there's definitely an outward push. So this is vector addition of forces. And the question is how to keep the walls from being pushed apart. Question. How to keep the walls from falling outward. Okay. Being pushed apart, that's the question mark. Okay, what comes after this? I think we'll do one more. Post and lintel right here, that's the first one. Second one, we've got the gable. So yeah, you want to get some gable images too. Of course you could draw a nice one there, but see what you find also to illustrate it. So the third one is going to be the arch, and in particular the Roman arch. So 3, arch, Roman arch. And this one is based on a semicircle. So we'll take, actually, if we did an entire circle and just took half of it, that would be our semicircle. And we'll go ahead and do another one around it. We can imagine this being made out of some cut stones or something. And let's have a look. If these are cut stones, we get to the really important one here. And I'm going to accentuate this. This one right here is called the keystone. So the keystone so you guys go ahead and look up Roman arch, get some images. Keystone is very important. The keystone has that tapered shape, okay? And now the vector nature of the force is clear because this pressure is acting at this downward angle, okay? And so ideally, if all of these are adequately together, then this one can't fall through, right? It can't fall through because everything is pressing against each other. This one's pressing down at that angle, right? So you definitely want to accentuate that tapered shape of the keystone. Of course, there's still a problem. You're trying to get your forces to go down along the arch all the way to the ground, and there's a tendency for the arch to buckle, okay? And the way the Roman arch gets over that tendency is just to build it very, very thick. Another thing that can be done with the Roman arch is to have a second one, okay? And maybe you put a road on top, and then the buckling tendency of one is captured by the buckling tendency of this one, and they hold each other up, okay? So you've got your Roman arch, and I'll just give you some interesting ideas to look at. So bridges, aqueducts, and then just in their basic architecture of buildings as well, you'll see a lot of Roman arches. So now that you see the vector nature of the compressions in the Roman arch, you can appreciate that, and go ahead and look some of these up as well. So I think that's what we're going to end with today. These three. And yeah, you guys have a chance to look some of this up, get some nice pictures. Of course, if you're a really good artist, you can draw some nice pictures too. But you can download some pictures, and you want to, you've got the keystone concept you want to have a good look at, and then Roman arch with bridges, aqueducts, We're going to have a few more of these elements before we're done, but this is a good place for us to stop now, okay? So the homework, we had those numbers, we had the vector Pythagorean calculation, and then we have the images that are just going to make your notebook very interesting, okay? Of these three structural elements, the post and lintel, gable, and then the Roman arch. A lot of stuff here. Good, see you guys next time.